Hello kitties, we are back and we're going to be continuing our discoveries of the kinematic equations, but this time we're going to add the fact that gravity on the surface of the Earth makes things fall at 9.8 meters per second squared. Okay, I don't know if you can see that well. But, yes, and later, I'm just giving you the facts right now. Kinematic equations, it's like an introduction to physics, okay? The kinematic equations unit is going to be pretty much an introduction to classical mechanics, okay? And we're going to be learning how to derive these and why these equations pop up in the first place. But for now, we're going to focus on why, or that. So if we're to drop a ball, let's say that we had like a ball in our hand, or let's say that we had a penny in our hand, and I drop it, it's going to drop at 9.8 meters per second squared, regardless of the mass. And we're going to be showing why that is later on in the series in classical mechanics. But just remember that this Sharpie and this penny are going to drop at the exact same rate. Because the Sharpie is more massive, that has nothing to do with it. They're both going to drop at the exact same rate. I don't know if you can see that. Of course, the Sharpie is going to have slightly more friction on the air, more drag. So, if you go into a planet and it has, let's say that we took, so if we had a planet and it had no atmosphere, had no air, and we dropped the Sharpie, there's the Sharpie, or let's say that's just a stick and a point, and the stick is more massive. The stick and the ball are going to drop at the exact same rate acceleration. And you can tell that the 9.8 meters per second squared, this only applies to Earth because, well, this does actually depend on the mass of one of the objects. The larger object will, that's how we'll, if we take the mass of the larger object into consideration, that's how we'll get this acceleration. This is how fast we're accelerating toward the larger object. So if we have, like, Mars, and we're accelerating, we're the less massive object, and we're accelerating toward, let's say that this is Mars. I don't know what the acceleration due to gravity is on Mars, but it'd be less than on Earth. Okay, so now how do we apply this to our kinematic equations? Well, now with our kinematic equations, we can, let's say that we have, well, I'll show you. Let's say that we have a boy. Okay, hi. And he's going to be, hi. Okay, and, oh wow, I don't know if you can see it that well. Oh well, you can deal with it. And he is going to be throwing here's a graph, and where h is height, and he's going to be throwing, and this is going to be time, okay? And so he's going to be throwing the ball up, just straight up, okay? And if we want to graph this, because time is always moving forward, it would look like this, right? This is what the graph would look like. And let's draw arrows to show where it's going. Okay? Okay, so now we're going to use our kinematic, or specifically we're going to use the final velocity is equal to the initial velocity plus acceleration times time. Do you remember that kinematic equation? Well, we're going to use it now. Okay, so let's say that we know that he's throwing the ball upward at 50 miles an hour. 50 miles per hour. That's the upward force. Okay? Now, let's say that when it reaches the bottom, because, okay, so if we look at this parabola, that this path that it'll take will always be symmetrical, like this, okay? There's its line of symmetry, which means that its velocity going up at the beginning will also be its velocity at that same height coming down. So which means that its initial velocity will also be 50 miles per hour. Alright, but this is going to be negative because we're going downward, not upward. Okay? So, and then the acceleration, because we're acknowledging that acceleration is going to be the same for all objects, 9.8 meters per second on Earth. So we're going to do this, 9.8 meters per second squared. And actually, let me rewrite this, because I'm doing this in miles per hour, and that messed me up last time. That's a bad thing to do. Don't do that. Okay, so we're going to do this. The final velocity is going to be equal to, say, let's say 60 meters per second squared. That's actually pretty fast. And let's say that the initial velocity is also going to be 60 meters per second. Or it's not squared because it's not accelerating. These are velocity. And I'll be showing you, because acceleration is change in velocity in time. So, and we're going to get into that when we start looking at derivatives of motion, or time derivatives of stuff. So this is the information that we have, and I want to find how long it'll take for the ball to go up and then back down. So what are we going to do? We're going to plug all these things into our equation. Okay. So, and we're going to do, so the final velocity, which is going to be the velocity right here, is going to be negative 60, right? Because it's going down, negative 60 meters per second squared. Okay, this is getting blurry. I will move this up so you can see it maybe a little bit better. Okay. Still a little blurry, but deal with it. Is equal to the initial velocity, which is 60 meters per second squared. And then we are going to be adding, because the acceleration due to gravity is downward, we all fall downward, hopefully. Then we got negative 9.8 meters per second squared. Okay, and the square, we have the square at the end of seconds, that's only because it's accelerating, and it creates this parabola shape. And then we have the oh god, you can't see this very well. That didn't help. Okay, so you're gonna deal with it like I said before. And then we have the time, which we don't know the time yet, and we're gonna have to solve for the time. Okay, so now let's do 60. So let's move this to the opposite side. So we subtract 60 from both sides. Minus 60 miles per, or meters per second, is going to be equal to negative 120 meters per second squared. And that is going to be equal, because right, we're subtracting 60 from both sides. MPS. Or not squared. Why am I putting squared at the end of these? These are, it's velocity. Okay, so now we're going to take, so now this is equal to negative 9.8 times t, which means that we're going to take negative 120 meters per second squared and divide that by negative 9.8, and you can see why hopefully we should have a negative number. Both of these should be negative because it's weird to have negative time. Okay, so 120 divided by 9.8, you can't really see this that well, but God, my keyboard's in my way. Let me get out my calculator. I'm doing this on my computer, so you can't see it. So everybody take out their calculator, and you should take negative 120. Or actually, it doesn't matter. Just do 120. God, 120, and you divide that by 9.8, and you get the time, which is 12.225 approximately. So this is approximately equal to 12.225. And because we're doing this in meters per second, this is going to be 2.225 seconds. And that's how long the ball's going to take to go up and then go back down. And that's our unit on free fall. Hope you enjoyed this lesson. My name is Yuichi Gray, right, from Salutary Spade Science, and I am signing off now.